Hi, welcome to Concept Based. I'm John Hepworth. This one's for Year 11 Advanced students. We're still in the Working with Functions section of your syllabus, and inside that section today I'm focusing on quadratic and cubic functions, just the quadratics for today. This will be the only quadratic video that I make in this section, as there is lots in your syllabus to come in working with functions, reciprocal functions, constructing and using functions, direct and inverse functions, circles and semicircles, and so on. There's a lot there. And although quadratics are very, very important and come up often, you should have done extensive work on these in year 10. So if there could be more work put into looking at other parts of this function topic. However, if you are looking for some support in this section, then feel free to reach out, info@concept-base.com.au. But let's have a look at one question today. And the idea of this question is to see if I can make you go, oh, I didn't think of it like that before. Something new that you might add to your repertoire of being able to graph quadratics and tools you can use. And the reason why that comes up in this question is particularly around the vertex. You may have some ideas that you use about the vertex, but I want to show you something new, well, maybe new today, that might draw some things together for you. So the question here is, express y equals x squared minus 2x plus 3 in the form y equals x minus alpha squared plus c, then determine the coordinates of the vertex and graph the function. Okay, seems pretty straightforward. There is a few things that we need to do here. So let's get cracking. Not to quote another YouTube channel. First of all, can you identify what it is that you need to do to go from the form y equals x squared minus 2x plus 3 into some squared term plus c? If you can't, again, you'll need to review a bunch of your year 10 content, because what we want is that you will look at that and you'll identify that if you have brackets with a square, that's some sort of perfect square. And that's come from somewhere. And we can always create these perfect squares by completing the square. So if you didn't identify that that was the step between those two, then again, revision might be necessary. So we're going to go ahead and we're going to complete the square. That's not even close to the question. That's better. We're going to go and complete the square on this. So completing the square, we're going to halve the middle term and then square it and then add it on so it does make it a perfect square. So we are going to halve -2, and half of -2 is -1. We're going to square it and that gives us 1. So we need a +1 at the back here. And then once we've got the +1 here, we then need to remove that 1 because we can't just add things into algebraic equations and not do anything about it. That would change the question completely. And our +3 is still hanging around at the back here. What we're going to do is factorize this bit into our perfect square. So we get x. We take this sign here as the sign in our perfect square. And this one's a minus. And then it's this back term here that is going to be squared. So we take the square root of it, but the square root of 1 doesn't change it. It's still x minus 1 squared. But if there was a 2 back there, be careful. It would be root 2 you'd be taking. Or if it was 4, you'd be taking 2. Make sure you take the square root of that last term, because obviously if you expand this bracket, it's going to be the last term times the last term to get to where we were. And -1 plus 3 is 2. So we have now completely rearranged this equation, this function even, into this new form. Now, what might be confusing or what might be something new to think about here is that this is not an expression of linear factors. Okay, we're not multiplying by just linear factors here. So therefore, that the null factor theorem doesn't actually hold here. You know, I can't go ahead and say that 1 is a root of this equation. Let's just check that that is true, right? Because 1 is a factor there. But if we go and substitute 1 into this equation, we would get 1 squared minus 2 times 1 plus 3, which is 1 minus 2 plus 3, and 1 minus 2 is -1 plus 3 is 2, which is not a factor, which is not a 0, okay? So it doesn't work. So what are we going to do about the fact that we've got this? And the question I'm asking here, or the thing that I want to draw out that's possible here, is that you sort of can think of it as a factor or a zero of the function, but you have to think of it at a special location. And the location that I'm going to take to think about it comes from this back part here. What if I considered the graph where y equaled 2? So here if I make 2, so y is equal to 2, what would I end up with? So if I do this, obviously now I can subtract 2 from both sides, and I end up with 0 equals x minus 1 squared. So I now actually have a double root at 1 when the y value was 2. So I'm thinking of this still in the way that I think of zeros in a function, but I'm moving it up the graph a little bit. So I now have an understanding of what's going on at x equals 1 and y equals 2. So let's go and have a little look. Oh, there's some old working out. Let's go and have a little look at at a graph of what this is going to start looking like. So if we now go and graph this, we know at 1, y's up at 2, and this point exists. But we know more than the fact that this point exists. We know that this is creating like a double zero, but it's not a zero, it's at 2, but it's still a double. And so with it being a double, we identify that the parabola is actually turning around at this point. So now, if we go back up the top and just check, what sort of parabola is it? Well, it's positive. We have a leading positive coefficient. It's turning around at this point. We also have this plus 3 y-intercept. So we can go down here and we can actually put, at 3, a y-intercept, a bounce here at 1, 2, and we can try and draw a nice smooth parabola like this. So this is, you know, we've drawn this extensively. We've drawn a lot of this graph just by changing it into this form, but then not thinking of it in that form as not being zeros or not being factors. We've just moved the whole thing up by 2 and taken this y equals 2 line into consideration and sort of treated that line as the x-axis and then looked at what the factors would be on that line. So that's why we've got this bounce here because of this double root at 1, 2, and we're able to draw that parabola. Now the question actually said, express it in this form, then determine the coordinates of the vertex. Now I already have determined the coordinates of the vertex just by doing what I did at that line 2. But of course, you have a formal way of determining what the vertex is. Excuse me. So let's use that formal procedural way and see what it says for our understanding way that we did earlier. So we have a formula for finding the axis of symmetry, and that tells us that x equals negative b over 2a. And back out of our quadratic, b is negative 2 and a is 1. So we get negative 2 over 2 times 1, which gives us 2 over 2, which is at 1. So our axis of symmetry is at x equals 1 here, which is what we found already. And then once we know that x equals 1, we chuck that back into our equation. Now we could put this back up into the original one or into this one that we found. If we put it into the one that we found, then we're going to get a 0 out of this part, and we're going to just get a plus 2. So we're going to get 1 minus 1 squared, which is nothing squared, plus 2 equals 2. And so now we, by equation method, have confirmed that our vertex is at the point that we thought it was at earlier. So I just want you to have this skill set where you don't always have to be working on the x-axis to think about factors. You can have the whole thing shifted up and then deal with it up there when you've changed the y value so that you can subtract away a constant and then work with the factors at that point. And everything is still true. Like this could be for a cubic or any polynomial, and you'd still know whether your factors are going through, whether they're bouncing, whether they're a twist. It's all the same because we're using the same concepts of those factors. It's just moved a little bit. So don't be afraid of working with your graphs, not necessarily just on the x-axis. Have to have an understanding of how they can work when they're shifted a little bit as well. Now that gets more formalized in the future in your course, but it's even something that you could have been working with in year 10, and it's definitely something that you can utilize there in year 11. It then says, of course, to go ahead and graph the function. We've already graphed it. And, you know, if I was being a good student of mine, I probably would have tried to sketch this before I even went and did any of this algebraic working out. Now, one thing that may have popped up if I would have tried to sketch it first is I would have been looking to see whether or not the equation had any roots. And so if we go back to this original equation and we take into consideration the discriminant, the b squared minus 4ac to see how many solutions this quadratic has, b squared is 4 minus 4 times 1 times 3, which is 12, is negative 8. And we have nothing, we have a negative discriminant, so there are no solutions. So if we have no solutions, there are other tools that we can use, such as the one that I did, to find where this graph actually goes without having to delve into formulas of the axis of symmetry and hence the vertex point that is on that graph. So just something that you can take into consideration. Don't always consider when y equals 0. Sometimes you could consider when y equals 2 or when y equals whatever you need it to equal as a constant to get rid of something so you can focus on the parts that appear to be, we'll call them factors, but they're not, just things that describe how the graph works on that line.